Let's go ahead and take a look here at example number 1 to see how we can start to model different functions with a power series. So example 1 here says, find a power series representation for g of x equals 1 over 2 plus x. So again, if I was to graph this function, it has some picture, and I'm interested if there's a power series, one of these like infinitely long polynomial things that might look just like it. But I also want to know an interval of convergence, like where would this power series actually look like this function? So in order to try to go ahead and do this, I might notice something like the following. Here's where I can start. So I'll start by at least noting at first that g of x resembles the sum of a geometric series. Okay? If you take a look at the basic structure, you can see we kind of have this like a over 1 minus r. The weird part here is I might have to do a little bit of manipulation to fully be able to see that. So notice here I could rewrite this as 1 over 2 minus negative x. That at least gets me with the value of a and then something kind of like a 1 minus an r. So it seems like negative x right now might be something like the r, but I have to adjust for this 2 here. And that's actually not too difficult to do. I might be able to go ahead and maybe divide everything on top and bottom here by a 2. And if I was to do that, you'll notice that I'll end up with the following. So this right here is equivalent to g of x. And with this, I might then be able to fully see why I might call this the sum of a geometric series. Okay? So I'll write over here that we see that g of x is equivalent to, again, it's a half over 1 minus the quantity, negative x over 2. And I can then say that, again, this looks like the sum of, just fix that, of a geometric series provided that the absolute value of my r, which in this case looks like my negative x over 2, is less than 1. So remember that in order to be able to have a geometric series converge to something, I had to have my absolute value of r be less than 1. And so I can check to see when exactly this might apply. Now what I'll notice right away is that if I attempt to simplify this statement, the negative in there isn't really going to matter. Because if I'm going to absolute value, I'm going to have to remove that negative anyways. But notice that since x might still be negative, I actually need to keep these absolute value bars. Of course now, we know that I can rewrite this as x over 2 being wedged between negative 1 and positive 1. And if I now multiply everything through by 2, I can see what x actually has to exist between. So this is kind of a really powerful idea. We've seen here that we have, again, a geometric series. We can kind of see up here a value of a. We can see down here a value of r, so this looks like the sum of something geometric. And we know that it would converge, a geometric series would converge to this as long as x was between negative 2 and positive 2. So what this really means is that we could go ahead and state the following. So we could say g of x, which again is equal to a half over 1 minus a negative x over 2, should be equal to this kind of a geometric series. Notice I'm going to write it in the basic geometric form of a times r to the power of n. Now don't be surprised here that I'm not writing n minus 1, because I'm having my series start at n equals 0. Remember that with every geometric, the first value that the power should take on should be 0. So since this is n is equal to 0 down here, I only need power n. If this was n is a 1, then I would need power n minus 1. But I'm just going to write it like this. So this here is a really, really powerful idea. I now have a series that looks just like my g of x function, and its interval of convergence is negative 2 to 2. Now again, I'm going to ask you to go ahead and try to use your calculator to confirm for yourself that if you were to actually go to your calculator, type in this function for your g of x, and then start typing in some of the terms of this series, I bet that on the interval from negative 2 to 2, they're going to start to look unbelievably similar. So this is kind of a really cool process that we're seeing here. We can oftentimes look at a function, and if it seems to resemble the basic structure of something geometric, like the sum of something geometric, we might be able to work with this and kind of get back to a geometric series that it's equivalent to. So this is going to be a really powerful technique. In fact, in the next video, we're going to take a look at another example here where you can go ahead and try to work with a function that also has the same basic shape.